And before this night is through, you'll understand precisely why. And the answer is stranger than most people ever expect. Consider first the nature of what we know and what we assume. Most individuals operate within a framework of understanding that has been constructed over decades, refined through education and experience, validated by peers and institutions. These frameworks are comfortable. They make sense within the context of our daily lives and the information we've been given access to. But frameworks, by definition, have limitations. They exist within boundaries, and when something falls outside those boundaries, when evidence contradicts the foundational assumptions upon which an entire understanding has been built, the human mind experiences a particular kind of resistance. This resistance is not irrational. It is, in fact, a perfectly logical response to information that challenges the very structure by which we interpret reality itself. What you're about to learn exists in precisely that space outside the boundaries. It has existed there for longer than most historical documents suggest. The mechanisms that kept this knowledge compartmentalized were not crude or obvious. They were sophisticated. They relied on a basic principle that no one would believe the truth even if it were presented to them directly. This principle has proven remarkably effective throughout history. There are documented cases of individuals discovering or witnessing these phenomena, only to be dismissed by colleagues, ridiculed in academic circles, or simply ignored by institutions designed to maintain the current understanding of how the world operates. The strangeness begins with a simple observation. Certain patterns repeat throughout human history at intervals that are too precise to be coincidental. These patterns appear in different cultures, separated by thousands of miles and centuries of time. They appear in architecture, in mythology, in astronomical records, in geological formations. When examined individually, each instance can be explained away through conventional means. Coincidence is a powerful explanatory tool. It requires no further investigation. It provides closure. But when the patterns are mapped together, when the intervals are measured and the occurrences are plotted, a structure emerges that defies the comfortable frameworks we've constructed. This structure suggests intentionality. It suggests planning. It suggests the involvement of agents with capabilities and timescales that extended far beyond what conventional history acknowledges. The evidence for this exists in multiple forms. There are physical artifacts, some housed in museums under innocuous classifications, others carefully removed from public access altogether. There are texts, both ancient and surprisingly recent, that describe phenomena in technical language that should not have existed in the periods during which they were written. There are witness accounts from credible sources: scientists, military personnel, government officials, individuals whose professional standing and documented accuracy make their testimonies difficult to dismiss without engaging with the actual content of what they described. There are also absences in the historical record, gaps where documentation should exist but does not, periods of history that are surprisingly poorly documented given their presumed importance. These absences are significant. They suggest deliberate curation of the historical narrative. What makes this particular night different is that the threshold has been reached. The conditions that have historically maintained the compartmentalization of this knowledge have begun to fail. This is not a matter of opinion or belief. It is observable in measurable ways. The information that would have been impossible to verify a decade ago can now be cross-referenced through multiple independent sources. Individuals who would have been isolated in their discoveries can now find each other across geographic boundaries. The mechanisms of control, which relied heavily on isolation and information scarcity, have become exponentially less effective in an environment of information abundance. This creates a particular moment in time where revelation becomes possible. It is a moment that those who understand the full scope of this knowledge have anticipated and prepared for. The answer you're approaching is stranger, because it operates on a scale and timeline that makes most human-conceived narratives seem parochial. It involves consideration of phenomena that intersect with what we call physics, what we call biology, what we call history, and what we call mathematics. It requires the temporary suspension of categorical thinking that separates these disciplines into distinct domains. It demands recognition that the universe operates according to principles that are simultaneously far more complex and far more elegant than the current fragmented scientific understanding allows. It presents a version of human history in which certain crucial events were not accidents or the product of random human agency, but rather were directed occurrences, managed with a vision that implies oversight and purpose. The implications of understanding this fully extend beyond mere intellectual satisfaction. They reshape how one understands one's place within the structure of reality itself. They alter the fundamental assumptions upon which personal and collective decision-making is based. They suggest that certain futures are possible because certain pasts were deliberately constructed. They indicate that understanding the true nature of our origin is essential to determining the actual range of our possibilities. But none of this will remain abstract or theoretical. Before this night concludes, you will have access to the specific evidence. You will see the documentation. You will understand the mechanisms. You will comprehend why the answer to why this is happening is stranger than most people ever expect, and you will recognize why it had to be presented to you in precisely this way. Let's start with what we actually mean when we say the universe is empty, because there are two different things going on, and most people conflate them. The first type is physical emptiness, the vacuum of space. Between stars, between galaxies, between you and the next nearest atom if you were floating somewhere in the intergalactic void, there is essentially nothing. Not thin air, not a gentle breeze of particles, nothing. The best vacuum we can produce in a laboratory on Earth still contains billions of atoms per cubic meter. Interstellar space contains roughly 1 atom per cubic centimeter. Intergalactic space contains far less than that. We're talking about an absence so complete that the word empty barely covers it. There's no human experience that maps onto this. It's not like a room with the furniture removed. It's something closer to the total elimination of the concept of substance. The second type is structural emptiness. This is different. This is about how matter, the small amount that does exist, is arranged across the universe. And here's the thing most people don't realize. Even if you gathered up every atom in the observable universe and started mapping where it all sits, you would find that matter is not spread evenly. It's clustered into thin filaments and sheets, with enormous hollow regions between them. That structural emptiness, those vast voids between the filaments, is what we'll get to in the next section. But first, let's make the physical emptiness feel real. because most people genuinely underestimate how extreme it is even in the parts of the universe that feel busy, like the inside of a galaxy. Start with our own solar neighborhood. The nearest star beyond our Sun is Alpha Centauri. It sits about 25 trillion miles away, roughly 4.24 light-years. That's the distance light covers in 4 years, traveling at 186,000 miles per second. Just holding that number in your head for a moment. 25 trillion miles. And that is our next-door neighbor, the closest star, our cosmic backyard. That's what close looks like out here. Now think about what that means for the interior of the Milky Way. Our galaxy contains somewhere between 200 and 400 billion stars. You might picture them as tightly packed, like a dense crowd. They are not. If you shrunk the Sun down to the size of a grapefruit, on that same scale, Alpha Centauri would sit roughly 1,500 miles away. Not 1,500 feet, not 1,500 yards. Thousands of miles, for what is essentially our nearest neighbor, on a scale where the Sun is small enough to hold in your hand. The Milky Way, on that same scale, would span a distance so vast it wouldn't fit inside the solar system. Every single star in our galaxy, separated from every other by those same crushing distances. A galaxy of hundreds of billions of stars, and most of its volume, is empty. To put that scale in another way, if you could somehow travel at 1 million miles per hour, speeds that would take a spacecraft roughly 7 hours to reach the Moon, it would still take you more than 2,800 years to reach Alpha Centauri. Our nearest stellar neighbor would be a multi-millennium journey away. Yet this is what we call the cosmic neighborhood. Within our solar system, where the Sun and planets orbit in relatively tight proximity, there is still vastness beyond measure. The space between planetary orbits, once you leave the inner solar system, stretches across millions of miles with relatively little in between. But even that pales compared to the distances to other stars. This is the scale at which galaxies exist, not as crowded fields, but as archipelagos separated by oceans of action, vacuum. The Sun and its 8 planets, for all the complexity of the solar system, represent an infinitesimally small cluster in a cosmos defined by separation. Here's where things get uncomfortable. That's just the inside of one galaxy. Now zoom out. The Milky Way and the Andromeda Galaxy are gravitationally bound to each other. They are, in the context of the universe, practically on top of one another. Andromeda sits about 2.5 million light-years away. That's 2.5 million times the distance that light travels in a single year. The space between these two galaxies, 2.5 million light-years of it, contains almost nothing. A scattering of dwarf galaxies, some diffuse gas, and that's it. Beyond our local group, the distances between galaxy clusters climb into the tens and hundreds of millions of light-years, with the gaps between them containing even less. Now multiply that out. The observable universe has a radius of about 46 billion light-years. Inside that sphere, there are an estimated 2 trillion galaxies. That sounds like an enormous number. It is an enormous number. But spread 2 trillion anything across a sphere 46 billion light-years wide, and you begin to understand that even galaxies, for all their billions of stars, are specks separated by incomprehensible gulfs of nothing. The average distance between galaxies across the universe is on the order of millions of light years. Most of the volume of the observable universe contains no stars, no planets, no gas clouds dense enough to matter. Just an unbroken vacuum, cold and dark and extending in every direction farther than any spacecraft we have ever built could reach in any human time frame. This is what we mean by empty, not the casual emptiness of a clear sky, something qualitatively different, a kind of absence that our brains, evolved to track predators across a savanna, were simply not built to process. When you look at a clear night sky and feel like you're gazing into a vast open space, you're actually looking through a tiny, crowded sliver of the Milky Way. Everything beyond is the void. Alpha Centauri, at 25 trillion miles, is right there by cosmic standards. And even it is so far away that our fastest spacecraft would take over 6,000 years to reach it. The universe doesn't have empty patches. Emptiness is its default state. Matter, stars, planets, life, these are the exceptions. Rare local concentrations in an almost featureless expanse. The emptiness isn't dramatic in a visible way when you look up at night. The stars seem numerous, but visible stars are a trick of perspective. Bright points standing out against a background that is almost entirely dark matter and vacuum. Remove the ability of your eye to amplify points of light, and the sky would look like nothing at all. Black in every direction. That's the more accurate picture. That's closer to the truth of what's out there. And that's before we even start asking why the matter that does exist is arranged the way it is. To understand why the universe looks empty, you have to understand what astronomers call the cosmic web. And once you see it, you can't unsee it. Most people picture the universe the way you'd picture a snow globe. Matter scattered more or less evenly in every direction. Stars and galaxies distributed like flakes suspended in water. That picture is wrong. What we actually find when we map the large-scale structure of the universe is something far stranger. Matter is not spread evenly. It's concentrated into an enormous interconnected network of filaments, sheets, and dense nodes, and between those structures are vast regions containing almost nothing at all. The whole arrangement looks, at cosmological scales, like a three-dimensional spider's web, or if you prefer, like the structure of a sponge, where the solid material traces thin walls and tunnels, and the empty spaces between them dominate the total volume. Here's where things get a little uncomfortable for our intuitions. Astronomers and physicists have long worked with something called the cosmological principle. The idea is straightforward. On large enough scales, the universe looks roughly the same in every direction and from every location. It's homogeneous and isotropic. And on the very largest scales, that's actually true enough to be useful. If you zoom out far enough, the clustering evens out, and the universe does look broadly uniform. But the cosmological principle has real limits. At the scales we can actually observe in detail, the scales where galaxies and clusters and superclusters live, the universe is anything but uniform. The observed distribution of galaxies is deeply inhomogeneous. Some regions are packed with thousands of galaxies clustered tightly together. Other regions are almost completely empty. The cosmological principle tells you about the average, the The cosmic web tells you about the reality underneath that average. So what does this web actually look like? Imagine filaments of dark matter stretching across hundreds of millions of light years. These aren't thin threads, they're enormous structures, and galaxies form along them the way dew collects along the strands of a spider's web. Where filaments intersect, you get the densest nodes in the universe. Massive galaxy clusters containing hundreds or even thousands of galaxies pulled together by gravity into a single gravitational knot. Between the filaments are sheets and walls, flatter structures where matter is somewhat concentrated, but less so than in the filaments themselves. And between all of these, between the filaments, between the walls, between the clusters, are the voids. These are the empty spaces, and they're enormous. Some of them span hundreds of millions of light years from one side to the other. More on those shortly. But for now, understand that the voids aren't the gaps between nearby objects. They're immense bubbles of near-nothingness, and they make up the majority of the universe's total volume. The question you should be asking is, where did this structure come from? Why isn't matter just spread out evenly? The answer takes you all the way back to the earliest moments after the Big Bang. When the universe was very young, a fraction of a second old, conditions were almost perfectly uniform. Almost. There were tiny fluctuations in density, random quantum variations baked into the fabric of the early cosmos. We're talking about variations of roughly 1 part in 100,000. That's extraordinarily small. If you compressed the entire history of those early density differences into a temperature map, the variation you'd see would be less than 1/10 of a degree across the entire sky. We can actually see this map. It's called the cosmic microwave background, and it's the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. The CMB is almost perfectly smooth. Almost. Those tiny imperfections in the early universe were the seeds of everything you see today. Gravity is patient, and it had 13.8 billion years to work with. Regions that were very slightly denser than average had slightly stronger gravitational pull. They attracted nearby matter. As they accumulated more matter, their gravity increased. More matter fell in. The process is self-reinforcing. Dense regions became denser. Simultaneously, regions that were slightly below average density started losing matter to their denser neighbors. As they emptied out, their gravity weakened, and they lost matter faster. Sparse regions became sparser. What started as a variation of 1 part in 100,000 has been amplified by billions of years of gravitational sorting into the dramatic structure we see today. Filaments, clusters, walls, and voids. Dark matter played a central role in this process. And this is important because dark matter doesn't interact with light. It can't radiate away energy the way ordinary matter can. That means it collapsed under gravity faster and more efficiently than the ordinary visible matter we see in stars and galaxies. Dark matter formed the scaffolding first, the cosmic web you see in galaxy surveys, those filaments and nodes. Traces an underlying framework of dark matter that assembled itself before the first stars ever formed. Ordinary matter then fell into that pre-existing framework. Galaxies didn't create the filaments. Galaxies formed inside filaments that dark matter had already built. Think about the time scale for a moment. The filaments we observe today didn't appear overnight. They've been growing for nearly 14 billion years. Some of the largest filaments in the universe stretch for 300 or 400 million light years. Structures so vast that our entire Milky Way galaxy, 100,000 light years across, would be an almost imperceptibly small bead, threaded somewhere along them. The Laniakea supercluster, our own cosmic address, spans roughly 520 million light years and contains the mass of 100 quadrillion suns. And it's just one node in the larger web. Now step back and ask how much of the universe this web actually fills. The filaments and sheets and clusters, for all their dramatic scale, are thin. The voids between them are not. By current estimates, voids account for something like 80% of the total volume of the universe. The material world, all the galaxies, all the clusters, all the filaments, everything that contains matter in any significant concentration is squeezed into roughly 20% of the available volume. The cosmic web is not a structure that fills space. It's a structure that traces the boundaries of enormous empty regions. And here's the thing most people don't fully absorb when they first encounter this. The expansion of the universe is accelerating. That acceleration is driven by dark energy, and what it means for the cosmic web is that the voids are growing. Matter continues to drain out of void regions and into the surrounding filaments. The filaments pull matter in, the voids lose what little they have, and over time the contrast sharpens. The universe is sorting itself into denser and denser concentrations of matter, surrounded by larger and larger regions of near-total emptiness. This is not a static picture. It's an ongoing process, and it's moving in one direction only. The universe isn't uniformly sparse. It's extremely dense in some places and almost completely hollow in others. And the hollow parts are winning by volume. The most dramatic version of cosmic emptiness has a name: voids. Not empty in the way a room is empty after you've moved the furniture out. Not empty the way a field looks empty before the crops come in. Empty in a way that has no human equivalent, no analogy that fully works, no frame of reference from ordinary life that can prepare you for the scale of what we're actually talking about. Voids are regions of the universe containing almost no galaxies at all, stretching across distances so vast that the word vast stops meaning anything useful. They typically span somewhere between 10 and 100 megaparsecs. That translates to roughly 30 million to 300 million light years across. And here's where things get uncomfortable. These structures aren't rare anomalies scattered here and there throughout the cosmos. They make up approximately 80% of the total volume of the observable universe. The universe isn't mostly galaxies with some empty space between them. It's mostly void, with thin webs of galaxies threaded through the gaps. So how did we find them? For most of human history, we had no way of knowing these structures existed at all. The night sky showed us stars and eventually fuzzy patches that turned out to be distant galaxies. But the three-dimensional arrangement of those galaxies was invisible to us. That changed in the 1970s, when astronomers began conducting systematic redshift surveys, essentially measuring how fast distant galaxies were moving away from us, to calculate how far away they were. When you map enough galaxies with enough precision, the large-scale structure of the universe starts to emerge from the data. And what emerged surprised everyone. Instead of a roughly uniform scattering of galaxies throughout space, the surveys revealed enormous regions containing almost nothing. bordered by dense walls and filaments of galaxies packed tightly together. The first major voids were identified in the late 1970s. The discovery fundamentally changed how cosmologists thought about the structure of the universe. But no void captured the scientific imagination quite like the one discovered in 1981 while astronomers were conducting a survey of the constellation Boötes. They expected to find galaxies. What they found instead was an absence so dramatic it took time to accept the data wasn't wrong. The Boötes void is roughly 230 million light-years in diameter. Think about what that means. You could line up nearly 2,300 Milky Way galaxies end to end and still not cross it. A region that size, based on the average galaxy density of the surrounding universe, should contain thousands of galaxies. When astronomers counted the galaxies inside the Boötes void, they found only a handful, dozens, where thousands were expected. Some surveys have found the interior to be even more sparsely populated than initial observations suggested. The void is not perfectly empty, we'll get to that, but it is so dramatically underdense compared to its surroundings that calling it nearly empty is not an exaggerated ration. Here's something worth sitting with for a moment. Imagine you were somehow placed inside the Boötes void. No spacecraft, no instruments, just you and whatever platform you're standing on, dropped into the middle of that structure. You look around. In every direction, for hundreds of millions of light years, there is nothing. No galaxy visible to the naked eye. No faint smear of light on the horizon that might be a distant star cluster. Just blackness, complete and total, in every direction simultaneously. The night sky would be darker than anything we experience on Earth, darker than the most remote desert on the clearest night. The stars you'd see would be those within your own galaxy, if you were even in one. If you were positioned well inside the void, even that might not be guaranteed. The concept of a night sky full of stars, the thing humans have looked up at for our entire existence, would not apply. There would be nothing to see. That's not poetic language. That is the literal observational reality of standing inside a cosmic void. The Boötes void is large. The giant void is almost incomprehensibly larger. Discovered in 1987 through additional redshift surveys, it measures approximately 1.3 billion light-years across. Let that number land. 1.3 billion light-years. Our entire observable universe has a radius of about 46 billion light-years. One void takes up a meaningful fraction of that. The giant void makes the Boötes void look like a puddle next to a lake. Both structures exist within a universe that somehow still manages to surprise us with the scale of what it's built. Now, here's an important distinction, because precision matters here. Voids are not perfect vacuums. They're not completely empty of everything. Inside a void, you'd find diffuse gas spread at extremely low densities. The occasional dwarf galaxy clinging to existence with far fewer stars than the galaxies crowding the filaments. Dark matter, present but sparse compared to the concentrations outside. What makes a void is not absolute emptiness, but extreme underdensity, relative to the filaments and walls and nodes of the cosmic web. Voids are so depleted of matter that they function as enormous hollow spaces in the architecture of the universe. The contrast between the filaments and the voids is extreme enough that describing the voids as hollow is not misleading. It's the most accurate shorthand available. And those voids are not static. This is something that doesn't get enough attention. Voids grow. They expand over time, and they do so through a process that is almost elegant in its logic. Matter, under the influence of gravity, tends to flow toward regions of higher density. Filaments and walls, being denser than voids, pull matter toward themselves. That means matter that starts out inside a void is gradually stripped away, draining outward toward the surrounding structure, like water running down a slope toward a drain. As more matter leaves, the void becomes less dense. That makes it even less capable of holding on to what remains, which accelerates the outflow further. The expansion of the universe adds another layer to this. As space expands, the low-density interior of a void expands faster than the denser surrounding regions. This was because there's less gravitational resistance pulling back against the expansion. Voids effectively inflate while the filaments consolidate. The rich get richer, cosmologically speaking, and the empty get emptier. This process has been operating for nearly the entire age of the universe. The small density fluctuations that seeded the cosmic web, those 1 part in 100,000 temperature variations visible in the cosmic microwave background, were sorted by gravity over 13.8 billion years into the structure we observe today. What began as barely perceptible differences in density became the filaments and voids we now map in galaxy surveys. The voids that exist today are the direct descendants of those ancient underdense regions, grown enormous through billions of years of matter drainage and cosmic expansion. They are not accidents or gaps. They are a fundamental outcome of how the universe organizes itself. What makes voids so significant is precisely that 80% figure. Most treatments of the universe's structure emphasize the galaxies and clusters and filaments, the things we can see, the bright structures that dominate our maps. But by volume, those structures are the minority. The voids are the majority. The universe is not primarily a place of galaxies with some emptiness between them. It's primarily a place of emptiness, with some galaxies arranged in thin webs across the surface of that emptiness. The galaxies, for all their billions of stars and all the light they produce, are a thin skin on the outside of enormous hollow spaces. We live in one of the denser regions of the cosmic web, in a galaxy that sits within a supercluster. Even from here, when we look at the sky, we're mostly looking across voids. The Boötes void alone is large enough to make a person feel that scale has become meaningless. The giant void escalates that feeling to something closer to vertigo. And then you remember that there are thousands of voids mapped in the observable universe, ranging from smaller structures to these giants. That together they account for the vast majority of the space we can observe. The universe's most common feature, by volume, is not a star, not a planet, not a galaxy. It's nothing. By volume, the universe is mostly void, and those voids are getting larger as everything inside them continues to drain away into the surrounding filaments. Here's the thing that makes the emptiness question even stranger. Most of what makes up the universe is completely invisible to us. Think about that for a second. Everything you've ever seen, every star, every planet, every galaxy photographed by every telescope ever built, every glowing cloud of gas and dust stretching across light years of space, all of it, Every photon that has ever reached a human eye or a camera lens represents roughly 5% of what the universe actually contains. 5%. The other 95% is something we can't see, can't touch, can't directly detect with any instrument we've ever built. And here's where things get uncomfortable. That invisible 95% is not some minor footnote to the universe's story. It is the story. It is the reason the universe is structured the way it is. It is, in large part, why the emptiness looks the way it does. So what is it? Scientists break it into two categories. About 27% of the universe's total matter and energy content is something called dark matter. The remaining 68% is something called dark energy. Those two things together outweigh everything visible in the universe by a ratio of roughly 19-1. Every star you've ever seen in the night sky, every galaxy in the Hubble Deep Field Image, every nebula and asteroid and dust grain, all of that ordinary matter is a thin layer of foam on an ocean we can barely perceive. Dark matter is the less strange of the two, which is saying something. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. You could pass a beam of light directly through a wall of dark matter, and nothing would happen. No scattering, no absorption, nothing. By every electromagnetic measure we have, it is completely invisible. But it has mass, and mass means gravity. And gravity leaves fingerprints. The first serious evidence came from observing how galaxies rotate. Stars at the outer edges of spiral galaxies move much faster than they should, given the amount of visible matter those galaxies contain. If a galaxy contained only the matter we can see, the outer stars would move more slowly, like the outer planets of our solar system orbit the sun more slowly than the inner ones. But they don't slow down. They spin at speeds that only make sense if there's a massive invisible halo of additional matter surrounding every galaxy, adding gravitational pull that we can measure but can't see. The math doesn't work without it. Then there's gravitational lensing. Massive objects bend light. That's basic general relativity. When astronomers look at distant galaxy clusters, they sometimes see the light from even more distant objects stretched and distorted into arcs around the cluster, warped by the cluster's gravity like light passing through a lens. When you calculate how much mass is needed to bend light by that amount, the visible matter in the cluster falls dramatically short. Something else is there, something massive, something we can't see. That something is dark matter. And critically, dark matter is the scaffolding on which the cosmic web is built. Those filaments we talked about, those vast threads connecting galaxy clusters across hundreds of millions of light years, they're not primarily made of stars and gas. They're made of dark matter. The ordinary matter, the stuff that glows, just follows the dark matter's gravitational lead. Galaxies form in the densest regions of dark matter, where its gravity is strongest, and where ordinary matter collects fastest. The voids exist, where dark matter is sparse, because without that gravitational anchor, ordinary matter drifts elsewhere. The universe's large-scale structure, the web, the filaments, the clusters, the voids, is essentially a map of dark matter density, with visible galaxies as markers showing where that density peaks. Remove dark matter from the picture, and the cosmic web doesn't form. The universe would look completely different. So when you look at the emptiness of a void, that region hundreds of millions of light years across with almost no galaxies, you're not necessarily looking at a region with nothing in it. you're looking at a region with very little dark matter. The ordinary matter followed the dark matter out. The void is empty of what we can see. What it contains in terms of dark matter is a different question, and one we can't fully answer yet. Now multiply that strangeness by about 2.5, because dark energy is even harder to explain. Dark energy makes up roughly 68% of everything. And what is it? That's the honest answer. We don't know. What we do know is what it does. It drives the accelerating expansion of the universe. In 1998, 2 independent research teams were studying Type 1a supernovae, a specific class of stellar explosion that always burns at roughly the same brightness, which makes them useful as distance markers. If you know how bright something actually is, and you can measure how bright it appears, you can calculate how far away it is. The teams expected to measure a universe slowing down. After the Big Bang, gravity should be pulling everything back together, gradually applying the brakes to the expansion. Instead, both teams found that the expansion was speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than a decelerating universe would place them. The universe wasn't slowing down. It was accelerating. Something was pushing it. That something got named dark energy. It doesn't behave like matter. It doesn't clump. It doesn't concentrate in filaments. It appears to be a property of space itself. As space expands, the total amount of dark energy increases, which drives further expansion, which creates more space, which creates more dark energy. It's a self-reinforcing process, and it shows no sign of stopping. The accelerated expansion it's driving has been underway for roughly 5 billion years. Here's why that matters for the emptiness question. Dark energy is working against gravity at the largest scales. Gravity pulls matter together into filaments and clusters. Dark energy pulls space apart, stretching the distances between those structures, making the voids between them wider, and the regions outside our observable universe increasingly unreachable. If dark matter built the cosmic web, dark energy is slowly dismantling our ability to see it. The two invisible forces are pulling in opposite directions, with the universe's visible structure caught between them, and none of this is detectable through any conventional observation. You cannot point a telescope at a patch of sky and see dark matter. You cannot see dark energy. You can only infer them from their effects, the rotation curves of galaxies, the distortion of light, the accelerating recession of supernovae. The universe's dominant components leave no direct signal. They are not just dim, they are fundamentally undetectable by the methods we use to observe everything else. That's a different kind of problem entirely. What this means practically is that when we describe the universe as empty, we're making a statement about what we can see. We are not necessarily describing what is actually there. A region of space that appears completely void to every telescope we have might be threaded with dark matter filaments, sitting inside a field of dark energy, structured in ways we have no instruments to perceive. The emptiness may be, in part, a limitation of our senses and our tools, rather than a feature of the universe itself. The universe is not empty so much as it is opaque to us, in ways that go all the way down to the physics of how we observe anything at all. What looks like empty space might be threaded with dark matter and saturated with dark energy. We just have no way to see any of it. The universe isn't just sitting there full of emptiness. It's actively expanding. And that expansion is one of the primary reasons space looks so desolate when we try to observe it. Think about what that actually means. Not just that the universe is big and getting bigger, but that space itself, the fabric of reality between every object, is physically stretching. This isn't a metaphor. It isn't a poetic way of describing galaxies drifting apart like boats on a calm sea. The space between objects is genuinely growing, the way dough grows when you put a loaf of bread in the oven. Imagine pressing raisins into that dough before it bakes. As the dough rises, every raisin moves away from every other raisin. Not because any raisin is traveling through the dough, but because the dough itself is expanding. The raisins aren't going anywhere. The medium between them is growing. That's exactly what's happening to the galaxies in our universe. They're the raisins. Space is the dough, and the oven has been on for 13.8 billion years. This distinction matters enormously. When people first hear that galaxies are moving away from us, the natural assumption is that they must have been launched outward by the Big Bang, like shrapnel from an explosion, and are now coasting through space. That picture is wrong. Galaxies aren't moving through space away from us. Space itself is expanding between us and them, carrying them along for the ride. This is not a semantic difference. It has real physical consequences that determine what we can and cannot ever observe. The person who first measured this expansion wasn't even looking for it. In 1929, an astronomer named Edwin Hubble was cataloging the light from distant galaxies when he noticed something strange. The light from almost every galaxy he observed was shifted toward the red end of the spectrum. Red shifted. That shift has a cause. When a source of light moves away from you, the waves of light it emits get stretched out over the distance between you and the source. Longer wavelengths mean redder light. The more red shifted a galaxy's light was, Hubble found, the faster it appeared to be receding. And here's where it gets uncomfortable. The farther away a galaxy was, the faster it was moving away. This relationship, recession speed proportional to distance, is now called Hubble's law. It means that every galaxy in the universe is receding from every other galaxy, and the farther apart any two galaxies are, the faster the gap between them grows. There's no center to this expansion, no edge. From any galaxy in the universe, every other galaxy appears to be rushing away. We are not special in this regard. We just happen to be the ones asking the question. Now multiply that out. Close galaxies are receding slowly. Galaxies a billion light years away are receding faster. Galaxies 10 billion light years away are receding faster still. At some point, roughly 14 billion light years out, the expansion of space between us and those galaxies is happening so rapidly that the space is growing faster than light can cross it. Those galaxies are receding from us faster than the speed of light. And before you ask, no, this doesn't violate Einstein's relativity. Relativity says nothing can move through space faster than light. It says nothing about the rate at which space itself can expand. There's no speed limit on how fast the fabric of reality can stretch. Space doesn't have to obey the same rules as objects moving within it. Here's where things get uncomfortable. If a galaxy is so far away that space is expanding between us faster than light can travel, then any light that galaxy emits toward us will never reach us. It will spend its entire existence trying to cross a gap that is growing faster than it can move. It will never arrive. That galaxy is, for all practical purposes, gone. not destroyed, not dark, just permanently physically unreachable. Its light will wander through an expanding universe forever, never finding us. We will never see it. We will never know what's there. This is why the observable universe has a boundary. That boundary isn't a wall. It isn't a place where space ends. It's the distance beyond which light can no longer reach us given the current rate of expansion. The radius of that observable bubble is roughly 46 billion light-years in every direction. 46 billion light-years of galaxies, filaments, voids, and structure. And beyond that boundary, the universe keeps going, possibly forever. Some cosmological models suggest the total universe is vastly larger than the observable portion. Some suggest it's infinite. We don't know. We can't know. Because everything beyond that 46 billion light-year horizon is, by physics, permanently hidden from us. Not hidden by distance alone. Hidden by the rate at which space itself is running away. And it gets worse. The expansion of the universe isn't constant. It's accelerating. Dark energy, that mysterious force making up 68% of the universe's total energy, is pushing the expansion faster and faster over time. This means that some galaxies currently sitting inside our observable bubble will eventually be pushed beyond the horizon. Galaxies we can see today will, over the next tens of billions of years, recede to the point where their light can no longer reach us. They'll fade, redshift into invisibility, and vanish from our observable universe entirely. The number of galaxies we can observe is decreasing, slowly but irreversibly. The universe will not always look like this. It will look emptier, much emptier. Any civilization that arises in this galaxy a trillion years from now will look out and see almost nothing beyond their own local cluster of galaxies. The rest will be gone, swallowed by an expanding horizon they'd have no way to know existed. They might reasonably conclude the universe contains almost nothing. They'd be wrong, but they'd have no way to prove it. What this means for us right now is that the emptiness we observe isn't just a function of how matter is distributed. It's a function of what we can physically receive. Even if the universe beyond our observable bubble is packed with galaxies teeming with structure, filled with activity, we will never know. That information is permanently cut off from us. Not by any failure of technology, but by the laws of physics themselves. We live inside a bubble of light. Outside that bubble, space is expanding faster than light can travel, and no signal, no light, no information of any kind will ever cross that boundary in our direction. We are not just isolated by distance, we are isolated by physics. That isolation is not static, it's growing. The horizon is not fixed. As the expansion accelerates, the bubble accessible to us shrinks in terms of what we can ever hope to newly observe. We are in a universe that is, by its own physical rules, progressively closing off its most distant regions from our view. The emptiness we see when we look outward isn't only the emptiness of space as it currently exists. It's the emptiness of a cosmos that is actively pulling more of itself beyond our reach. Beyond a certain point, space between us and distant galaxies is growing faster than light can cross it, meaning those galaxies are gone from our universe forever, regardless of how powerful our telescopes become. Every moment you raise your eyes to study the nocturnal heavens, you're looking backward through time, and that fact has consequences for how empty the universe appears. This isn't a metaphor, it's a hard physical constraint. Light travels fast, about 186,000 miles per second, but the universe is so enormous that even at that speed, light takes a measurable amount of time to cross the distances between objects. And that travel time means every single thing you observe in the night sky is already history by the time it reaches your eyes. The star you're looking at might not even exist anymore. You'd have no way of knowing. Start with something close. The moon is roughly 240,000 miles away. Light takes about 1.3 seconds to travel from the moon to your eyes. So when you look at the moon, you're seeing it as it was just over a second ago. Not a meaningful gap, but scale that out to the sun, and the delay becomes 8 minutes. You're watching an 8-minute-old star when you look at sunrise. Now go farther. The Andromeda Galaxy is our nearest large galactic neighbor. It sits about 2.5 million light-years away. That means the light arriving at your eyes right now left Andromeda 2.5 million years ago. When that light began its journey, our ancestors were walking on 2 legs, but had not yet mastered fire. The galaxy you're seeing doesn't represent Andromeda today. It represents Andromeda as it existed in the early Stone Age of human prehistory. And Andromeda is practically next door by cosmic standards. Here's where things get genuinely uncomfortable. Push the telescope deeper into space, and you're not just looking farther away. You're looking farther back in time. Galaxies 5 billion light-years away appear to us as they were 5 billion years ago, before our sun even existed. Galaxies 10 billion light-years away show us a universe that was only about 3.8 billion years old. Young, chaotic, structurally immature. Those galaxies don't look quite like the ones nearby because they aren't. They're earlier versions of what galaxies become after billions of additional years of gravitational sorting and star formation. This is a crucial point that most people miss entirely. When astronomers look at the distant universe and say it appears different from the nearby universe, the first instinct is to wonder if that region of space is genuinely different. But that's not what's happening. You're not seeing a different place. You're seeing a different time. The nearby universe is showing you today. The distant universe is showing you the deep past. You're receiving 2 different eras of the same evolving cosmos simultaneously, just from different distances. It's as if you could stand in one spot and watch both a newborn and an 80-year-old, except you're told they're the same person. That's the view our telescopes give us every night. Now take that logic all the way out to the edge of what we can observe. The furthest thing we can detect is the cosmic microwave background, the CMB. This is light that was released roughly 380,000 years after the Big Bang, when the universe had finally cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was a hot, dense plasma, opaque like the inside of a star, and light couldn't travel freely through it. When those atoms formed, the plasma became transparent and light flooded out in all directions. That light is still traveling. We can detect it today as a faint glow of microwave radiation surrounding us from every direction in the sky. The CMB is the oldest light in the universe. There is no older light to find. And what does it show? Almost nothing. It's featureless, nearly perfectly uniform in every direction, with temperature variations of only about 1 part in 100,000. No galaxies, no filaments, no voids. No structure of any kind that would be recognizable compared to the universe we inhabit today. Just a faintly rippling curtain of ancient radiation from a time before stars existed. That uniformity is the key to understanding everything that came after. Those tiny temperature fluctuations, 1 part in 100,000, were the seeds of all structure in the universe. Regions slightly denser than average began pulling in more matter through gravity. Regions slightly less dense began losing matter to their neighbors. Over hundreds of millions of years, the density contrasts grew. Eventually, the first stars ignited inside the densest regions. Then galaxies formed, then clusters, then the vast filaments and voids of the cosmic web. The universe went from merely featureless plasma to the intricate structure we see today, and it took the full 13.8 billion years to get here. But here's what this means for why the universe looks empty. When you point a telescope at the distant sky, you're seeing different stages of that development process, all layered on top of each other. The nearby universe shows you the finished product, galaxies organized into filaments, with enormous voids between them. The mid-range universe shows you the structure still assembling itself, galaxies less organized, clusters less defined. The most distant observable universe shows you the raw ingredients before the assembly even began. The emptiness you see at the edge of the observable universe isn't emptiness caused by a lack of matter. It's emptiness caused by a lack of time. Gravity hadn't yet done the work of pulling matter into recognizable structures. This creates a strange observational reality. We don't see a single snapshot of the cosmos. We see a composite image assembled from light that left its sources across a span of over 13 billion years. Some of that light is showing us the universe as it is now. Some of it is showing us conditions that no longer exist anywhere. The deep sky is not a window. It's more like a geological record, with each layer representing a different period in cosmic history, and the deepest layers showing a universe that barely resembles the one we live in today. The universe we see isn't one universe at one moment. It's a stack of different eras of the same universe, with the most ancient layers being the most featureless and sparse. Our own galaxy isn't sitting still in this web of structure. It's being pulled, right now, toward one of the most massive gravitational concentrations within hundreds of millions of light years. That fact alone should stop you for a moment. We tend to picture our galaxy as a fixed address in the cosmos, a stable home sitting quietly among other galaxies. But the Milky Way is moving. It has been for billions of years, drawn towards something astronomers call the Great Attractor, and understanding what that thing actually is, why it exists, tells you something essential about why space looks so empty when you try to take it all in. Here's where things get uncomfortable. The Great Attractor isn't a single object. It's not a supermassive black hole sitting out there pulling everything toward it. It's a gravitational focal point, a region of space where matter has piled up to such an extreme degree that its combined gravitational pull extends across hundreds of millions of light years in every direction. Our galaxy, the Andromeda Galaxy, hundreds of thousands of other galaxies are all drifting toward it at roughly 600 kilometers per second. That's about 1.3 million miles per hour, not moving through space in any dramatic rocketing sense, just drifting, steadily, relentlessly, the way water drains toward a low point. The reason astronomers took so long to figure this out is almost absurd. The Great Attractor sits roughly 220 million light years away, in a direction that happens to be directly behind the densest part of our own galactic plane. Dust, gas, and the crowded stars of the Milky Way's core blocked our view almost completely for decades. We could see that something was pulling nearby galaxies off their expected paths, but we couldn't see what it was. It wasn't until X-ray and infrared telescopes could cut through the galactic dust that we finally got a clearer picture of what's hiding back there. What we found is staggering. The Great Attractor is the gravitational heart of a structure called the Laniakea supercluster. Laniakea is a Hawaiian word meaning immeasurable heaven. That name is not an exaggeration. Laniakea spans approximately 520 million light-years in diameter. It contains the mass of roughly 100 quadrillion suns. It is home to something on the order of 100,000 galaxies. Our own Milky Way is one of them. We don't live in the center of Laniakea. We live out near its edge, in a quieter region, being slowly drawn inward toward the concentration at the core. Think about what that means in terms of scale. Alpha Centauri, our nearest stellar neighbor, is about 4.24 light-years away. The distance that already feels crushingly far when you calculate how long it would take us to get there. Laniakea is 520 million light-years across. Alpha Centauri fits inside that distance so many times that the number stops having any intuitive meaning. And yet Laniakea, for all its staggering size, is just one supercluster among many. It connects to other superclusters along the filaments of the cosmic web, nodes in a network that extends across the entire observable universe. This is the hierarchy, and it's the key to understanding why space looks empty. Matter doesn't distribute itself randomly. It organizes into levels. Stars clump into galaxies under gravity. Galaxies pull toward each other and form groups and clusters. Clusters organize into superclusters. Superclusters align along the filaments we talked about earlier. At the junctions of those filaments, you get the densest concentrations of all. Places like the core of Laniakea, places like the Norma cluster sitting near the center of the Great Attractor. Each level of this hierarchy pulls matter in more tightly, concentrating it further. As matter concentrates in these structures, the regions between them lose material and become emptier. This is not a passive process. It's ongoing right now. The voids between filaments aren't just empty because matter happened to start out sparse there. They're emptying further because gravity is still at work, still pulling their remaining matter out toward the surrounding filaments and clusters. The universe is actively draining its own empty regions, pumping material toward the dense structures. Those dense structures are getting richer while the voids get poorer. Laniakea exists because gravity has been doing this for 13.8 billion years. The Great Attractor is the most extreme local expression of that process we can directly observe. There's something almost counterintuitive about what this means for the appearance of the universe. You might expect that the presence of a massive concentration like Laniakea would make space look fuller, not emptier. But here's the thing. A supercluster 520 million light-years across, containing 100,000 galaxies, still leaves an enormous amount of surrounding space nearly barren. The galaxies inside Laniakea aren't spread uniformly across that volume. They're bunched along filaments within the supercluster, clustered around its denser regions, huddled toward the gravitational center. The vast majority of the volume inside Laniakea is still largely empty, and outside of Laniakea, The voids stretching away in all directions are emptier than anything we discussed in the sections before this one. The Norma cluster at the heart of the Great Attractor contains more mass than most structures we could point to in our cosmic neighborhood. It sits approximately 220 million light-years away in a galaxy-rich region hidden behind our galactic plane. It anchors the gravitational well that organizes everything around it. Our galaxy will never actually fall into it in any dramatic sense. The accelerating expansion of the universe is working against the Great Attractor's gravity. Over timescales of tens of billions of years, even that gravitational pull won't be enough to hold Laniakea together as a coherent structure. Eventually, expansion wins, but right now, in this era of cosmic history, the Great Attractor is real. It is pulling on us. It is the most vivid illustration we have of how matter accumulates. That accumulation is the mechanism behind everything. It's why the filaments of the cosmic web are bright with galaxies, while the voids between them are dark. It's why the Milky Way exists as a galaxy at all, rather than as a diffuse cloud of scattered hydrogen. It's why you exist, on a rocky planet orbiting a star that formed inside one of those dense concentrations where matter was rich enough to build something. Gravity pulls matter together, and in doing so it hollows out everything around it. The universe's emptiness is not an accident of initial conditions. It's the direct result of gravity doing its job, concentrating matter into structures of increasing scale over billions of years. The spaces between them increasingly bare. Gravity's tendency to concentrate matter into ever larger structures is precisely what makes the spaces between those structures so profoundly empty. The physical emptiness of the universe is one thing, but there's a second layer of emptiness that's even harder to explain: the silence. We've spent the last several sections establishing just how physically sparse the universe is. The voids, the filaments, the vast stretches of near nothing between concentrations of matter. But there's a separate question sitting underneath all of that, and it's one that's bothered scientists since at least 1950. Given everything we know about how many stars exist, how common planets are, and how ancient the universe is, the cosmos should not be quiet. It should be loud, detectably, unmistakably loud. And yet here we are. Let's run the numbers, because the numbers are where this gets genuinely uncomfortable. The Milky Way alone contains somewhere between 200 and 400 billion stars. That's our galaxy. One galaxy. The observable universe contains an estimated 70 sextillion stars. That's a 7 followed by 22 zeros. For most of those stars, we now know planets are not the exception. They're the rule. Nearly every star we've looked at closely enough has planets orbiting it. Billions of those planets sit in what astronomers call the habitable zone, the orbital range where liquid water could exist on a rocky surface. We're not talking about a handful of candidates. We're talking about billions of potentially habitable worlds in our galaxy alone, and hundreds of billions across the observable universe. Now apply even conservative probability. Say only 1 in 1,000 habitable planets develops life of any kind. That still leaves hundreds of millions of life-bearing worlds in the Milky Way. Say only 1 in 1,000 of those eventually produces something we'd recognize as intelligent. That's still hundreds of thousands of civilizations. Say only 1 in 1,000 of those develops radio technology. You're still looking at hundreds of communicating civilizations, right here in our own galaxy, right now. The The math keeps pointing in one direction. The universe should be populated. It should be full of signals. It should be practically impossible to look at the sky and find nothing. And yet, in the summer of 1950, a physicist named Enrico Fermi was having lunch with colleagues at Los Alamos when the conversation turned to the possibility of extraterrestrial civilizations. By most accounts, Fermi had been quiet for a while, and then he looked up and asked a question that nobody in that room could answer satisfactorily. Where is everybody? It sounds almost too simple, but that question has never been resolved. And the more carefully you think through it, the more it refuses to go away. Here's what makes it so sharp. The universe is 13.8 billion years old. Our planet has only existed for about 4.5 billion of those years. That means there were civilizations that could theoretically have arisen a billion years before Earth even formed. Think about what a billion-year head start means. We went from stone tools to radio telescopes in roughly 10,000 years. A civilization with a billion extra years, even one that advanced at a fraction of our pace, should have had more than enough time to spread across the entire Milky Way. Not in some speculative sci-fi sense, but based on straightforward math. Even traveling at a tiny fraction of the speed of light, a civilization could colonize every star system in the galaxy within a few tens of millions of years. That's a small fraction of a billion. Any civilization with that kind of head start should be everywhere by now. But that's not even the threshold we're asking about. We're not asking for colonization. We're asking for a signal, a radio transmission, a laser pulse, a pattern in electromagnetic radiation that couldn't have been produced by any natural process, something that says, we exist. We've been actively scanning the sky for exactly that kind of signal for over 60 years, through programs grouped under the Search for Extraterrestrial Intelligence, SETI. The equipment has gotten better. The sky coverage has expanded. The signal processing capability we have today would have seemed impossibly powerful to the scientists who started this search in 1960, and the result has been the same every single year. Nothing. Not a whisper. Not an anomaly that held up to scrutiny. Not one repeating pattern that couldn't be explained by pulsars, quasars, or instrumental noise. The sky, when you listen to it, is filled with the natural radio emissions of stars, gas clouds, and distant galaxies. But intelligent signals? Zero. Here's where things get uncomfortable. This isn't just about radio. Radio is only one way a sufficiently advanced civilization might be detectable. A civilization that's been around for even 1,000,000 years, let alone 1,000,000,000, might be building structures visible at interstellar distances. Dyson spheres, for instance. Hypothetical megastructures that could harvest the energy output of an entire star. We've looked for those. Astronomers have specifically scanned thousands of stars for the infrared signatures that a Dyson sphere would produce. Nothing. We've looked for signs of stellar engineering, patterns of energy use that couldn't be explained by natural processes. Nothing. We've looked for signs of interstellar propulsion, for evidence of artificial objects moving between stars. Nothing. The apparent emptiness extends across every category of detection we've tried. It isn't that we've only looked in one place or with one method. It's that we've looked in many ways over many decades, and the answer keeps coming back the same. The galaxy appears to be empty of anything that didn't arise from purely natural processes. Now multiply that against the statistical case we just laid out. Hundreds of thousands of civilizations should exist in the Milky Way right now, based on even the most conservative assumptions. That number becomes billions if you use somewhat more optimistic parameters. Any of them older than us by even a few million years should have left traces we could find. Some should have had billions of years to expand, to build, to transmit. The contrast between what the math predicts and what we actually observe is stark enough to have a name: the Fermi Paradox. It's called a paradox because there's no obvious resolution. Both sides of it are defensible. The universe is old enough, large enough, and contains enough potentially habitable worlds that intelligence should be common. And yet every instrument we point at the sky comes back empty. These two things cannot both be straightforwardly true. One of them has to give. Either the universe is far less hospitable to intelligent life than the numbers suggest, or there's something about the nature of intelligent civilizations that explains why we can't detect them. Both possibilities are unsettling in their own way, and we'll get to those in the next section. But set the explanations aside for a moment. Just sit with the observation itself. We live in a galaxy with hundreds of billions of stars. We live in a universe with more stars than grains of sand on every beach and desert on Earth combined. Billions of those stars have planets. Billions of those planets orbit in the right temperature range for liquid water. The universe has had 13.8 billion years for something to happen on those worlds. And from all of that, across all of that time and scale and probability, we have heard nothing that we didn't produce ourselves. After 60 years of searching, we have found nothing. Not one confirmed signal, not one megastructure, not one piece of evidence that any other civilization has ever existed anywhere in our observable universe. The most unsettling possible answer to the Fermi Paradox is also the simplest one. The universe looks empty because it is empty, at least of intelligent life. That's a hard thing to sit with. We've spent the last several minutes building the statistical case. Hundreds of billions of stars in our galaxy alone. Trillions of potentially habitable worlds across the observable universe. Billions of years for evolution to do its work. The math seems overwhelming. Life should be everywhere, and yet the sky is silent. So either we're missing something about how look, or we're missing something about how rare we actually are. And here's where things get uncomfortable, because the second option has a serious scientific case behind it. An economist named Robin Hanson laid out the framework in 1998. He called it the Great Filter. The idea is straightforward. Somewhere on the path between simple chemistry and a civilization capable of spreading across a galaxy, there is a step, possibly several steps, that almost nothing gets through. A filter, a barrier so improbable, so statistically brutal, that across a universe containing trillions of worlds, almost no lineage of life ever crosses it. The question isn't whether the filter exists. Given the silence, it almost certainly does. The question is where it sits on that path, behind us or ahead of us. Think about what it takes to get from raw chemistry to a civilization that can build radio telescopes. First, you need life to start it all. Abiogenesis, the transition from non-living chemistry to a self-replicating molecule, has happened exactly once in our observable history. We have no idea how hard that step actually is. It might be nearly inevitable given the right conditions. It might be something that happens once every 100 billion years on any given world. We genuinely don't know. Then you need that simple life to make the leap to complex cells, eukaryotes with a nucleus, with mitochondria, with the internal machinery that makes multicellular life possible. That transition took almost 2 billion years on Earth. 2 billion years of bacteria, essentially going nowhere. That's not a fast process. That looks like a hard step. Then multicellularity. Then sexual reproduction, which dramatically accelerates evolution. Then complex nervous systems. Then language. Then technology. Each of these steps is a filter in its own right. Each one could be the barrier that explains the silence. If even one of these transitions is extraordinarily improbable, not just difficult, but genuinely rare on a cosmic scale, then the universe could be full of worlds covered in bacteria and completely barren of anything that thinks. Here's the thing most people don't realize. The great filter doesn't have to be one single catastrophic barrier. It could be the accumulated product of several steps, each individually rare, multiplying together into a probability so small it approaches zero across the entire observable universe. 1 in a billion, times 1 in a billion, times 1 in a billion. And suddenly, the math explains the silence without invoking anything exotic at all. But there's a second possibility. The filter might not be behind us. It might be ahead. That version is much harder to think about. It means the origin of life is relatively easy. The emergence of complex cells is manageable. Intelligence arises with some regularity. But then something happens. Civilizations reach a certain level of technological capability and they stop. Not because the physics gets too hard, because they destroy themselves. Nuclear weapons, engineered pathogens, climate collapse, some technology we haven't invented yet that turns out to be civilization ending. If the filter is ahead of us, then the silence isn't evidence that life is rare. It's evidence that intelligence is self-terminating, that the universe is littered with the ruins of civilizations that never made it past a certain threshold. That interpretation of the silence is not a comfortable one. If it's true, we are currently approaching the filter, and the silence of the sky is a warning, not a curiosity. Now, some scientists have pushed back on the framing of the Fermi Paradox itself. When you actually apply rigorous uncertainty estimates to the Drake equation, when you stop plugging in optimistic guesses and start acknowledging how little we know, the paradox softens considerably. Researchers have shown that under a reasonable range of scientific uncertainty, the probability of humanity being alone in the Milky Way is substantial. Not certain, not even likely in absolute terms, but far from negligible. The apparent tension between expectation and observation might simply be a product of overconfident assumptions about how common each step in the chain really is. And then there's the timing argument. This one doesn't get enough attention. The first stars in the universe formed from hydrogen and helium alone. That's it. Those were the only elements available after the Big Bang. No carbon, no oxygen, no silicon, no iron, no periodic table to speak of beyond the two lightest elements. There were no rocky planets around those early stars because there was no material to build them from. Rocky planets require heavy elements, and heavy elements are built inside stars through nuclear fusion and then scattered across space when those stars die. That process takes time, billions of years. The universe has to go through multiple generations of stellar birth and death before it accumulates enough heavy elements for complex chemistry to become possible. For most of the universe's history, its first several billion years, the conditions for life as we know it simply didn't exist. There was no substrate, no carbon-based chemistry, no rocky worlds. The cosmos was not yet ready. If you model when habitable rocky planets could first have formed in meaningful numbers, and when those planets could have hosted the long evolutionary timelines needed to produce technological life, you find that we may be genuinely early. Not the first. There are stars older than our sun with the right chemistry, but among the earliest generations of civilizations that could plausibly exist. The universe is cosmically young in terms of its capacity to host complex life. We might be sitting near the front of that wave. That framing reframes the silence entirely. It isn't necessarily that intelligence is vanishingly rare as an outcome. It might be that the universe hasn't had time yet to generate many instances of it. We are one of the early arrivals to a party that hasn't really started. The lights are still mostly off. The other guests haven't shown up yet, or they never will, because the filter is real and it's behind all of us. Both explanations lead to the same observable universe, quiet, dark, vast, and apparently empty of any other mind that has ever pointed a telescope at the sky or wondered what was out there. Whether the silence reflects early timing, accumulated improbability, or something darker waiting ahead of every civilization that reaches this point, the silence itself is the data. The universe has had 13.8 billion years to fill itself with signals, with megastructures, with the detectable exhaust of technological civilization, and it has produced none that we can find. The silence might not be a puzzle to solve. It might simply be the universe telling us something true about the rarity of minds capable of asking questions like this one. One of the most important things to understand about the apparent emptiness of the universe is that we can only see a tiny fraction of it, and that fraction is shrinking. That's not a poetic statement. It's a hard physical fact, and it changes everything about how you interpret the silence we've been talking about. When we look out at the cosmos and see mostly void, mostly darkness, mostly nothing, we're not seeing the universe. We're seeing a bubble defined not by walls or edges, but by the speed of light and the age of time itself. Here's how this works. The universe is approximately 13.8 billion years old. Light travels at a fixed speed, about 186,000 miles per second. That means we can only ever observe objects whose light has had enough time to reach us since the Big Bang. Anything beyond that distance is simply invisible to us, not faint, not hard to detect. Invisible in a way that no telescope, no matter how powerful, can ever overcome. The limitation isn't engineering, it's physics. You might expect that the edge of the observable universe would sit at about 13.8 billion light-years away, but it doesn't. It sits at roughly 46 billion light-years. The reason is expansion. Space has been stretching the entire time that light has been traveling toward us, carrying those distant sources farther away even as their light was in transit. The object that emitted the light we're receiving today was much closer when it emitted it. By now, it's been carried far beyond where that light originated. So the observable universe has a radius of about 46 billion light-years, not because anything traveled that far in 13.8 billion years, but because space itself has been doing the moving. That boundary is called the particle horizon. And beyond it, the universe continues. We don't know by how much. It could extend for hundreds of billions of light years. It could be infinite. There's no reason rooted in physics to believe the universe simply stops at the edge of what we can see. Beyond the particle horizon, there are almost certainly more galaxies, more filaments, more voids, more of the cosmic web we've been describing. And if intelligent life exists anywhere in the universe at all, the odds are reasonable that most of it lies out there, beyond our permanent reach, in a region of reality we can never access no matter what we build or how long we wait. That's an uncomfortable thought. We've spent decades scanning the sky for signals, cataloging galaxies, mapping the cosmic web across billions of light years, and all of that work covers only a sliver of what exists. Whatever is out there beyond 46 billion light years, we'll never know. But here's where things get even more uncomfortable. It's not just that we can't see everything now. It's that we're going to be able to see less and less as time goes on. The expansion of the universe isn't slowing down, it's accelerating. Dark energy is pushing space apart faster and faster, and the consequence of that is that galaxies which are currently visible to us will eventually recede beyond our horizon permanently. Their light, already traveling toward us, will lose ground to the expanding space between us. They'll redshift further and further, grow dimmer and dimmer, and eventually vanish entirely from our observable universe. This gives us something astronomers call the future visibility limit. Based on current measurements of the expansion rate, objects beyond roughly 62 billion light-years in co-moving distance are already beyond the point where their light will ever reach us in the future, even accounting for time. That boundary is fixed. Anything beyond it is already gone, whether we know it or not. And for the galaxies closer than that, they're on a countdown. The accelerating expansion will carry them beyond our horizon on timescales of tens of billions of years. Right now, we can observe hundreds of billions of galaxies spread across the observable universe. In tens of billions of years, an observer sitting in the Milky Way would see almost none of that. The entire visible cosmos would have shrunk down to our local group, the small cluster of a few dozen galaxies gravitationally bound to our own. Everything else, every other galaxy, every other structure, would have receded beyond the horizon and gone dark. Think about that for a moment. The universe we live in today, already mostly empty, would appear almost completely empty to any civilization that exists far in the future. They'd look out at the night sky and see almost nothing. They might not even be able to tell that the universe once contained hundreds of billions of observable galaxies. The evidence would be gone. The light would never arrive. This isolation is already underway. We happen to exist at a time when we can still see much of the universe's structure, when the evidence of the Big Bang still reaches us as the cosmic microwave background, when distant galaxies are still visible. But the window is closing. Slowly, on timescales that dwarf human history, the universe accessible to us is shrinking. The lights are going out, not because the stars are dying, though they will, but because the space between us and them is growing faster than the light they emit can cross it. What this means for the apparent emptiness question is significant. When we look out and see a mostly empty universe, we're already working with incomplete data. We're missing whatever lies beyond the particle horizon. We're watching galaxies that will eventually vanish from our sky. We're observing a cosmos in the process of becoming less observable. The emptiness we perceive is real, but it's also a measurement artifact of enormous scale. The universe is hiding most of itself from us, not through any conspiracy, but through pure geometry and the relentless arithmetic of expansion. The universe we can observe is not the universe. It's a bubble of light defined by physics, and that bubble will only get smaller as time goes on, and expansion carries more of the cosmos beyond our reach. So why is the observable universe so empty? We've covered a lot of ground to get here. Physical emptiness, the near-perfect vacuum of interstellar and intergalactic space, the staggering distances between stars that make Alpha Centauri at 25 trillion miles our closest neighbor. Structural emptiness, the cosmic web organizing matter into thin filaments, while leaving roughly 80% of the universe's volume as hollow voids, some of them hundreds of millions of light-years across. Observational emptiness, the hard boundary of the observable universe, a bubble defined by physics, not by telescope power, beyond which light will never reach us regardless of how long we wait. And then that final, quieter emptiness, the silence of the sky. 60 years of searching, nothing confirmed. Not one signal, not one megastructure, not one trace of anyone else asking these same questions anywhere in the observable universe. Put those together, and you get an answer that is technically complete, but somehow deeply unsatisfying. The universe is empty because gravity concentrates matter into filaments and leaves voids between them. It's empty because expansion stretches distances faster than light can cross them. It's empty because the observable bubble is finite and shrinking. It's empty because, as far as we can tell, intelligence is rare. Those answers are all true, and yet sitting with them feels different than just reading them. Because the question underneath the question isn't really about physics. It's about what any of this means for us. Here's where things get uncomfortable. We exist on a rocky planet roughly 8,000 miles across. That planet orbits one star among an estimated 200 to 400 billion stars in the Milky Way alone. The Milky Way is one galaxy among roughly 2 trillion in the observable universe. And the observable universe is a bubble 46 billion light-years in radius, which may itself be a vanishingly small fraction of a larger universe that extends beyond our reach forever. Our planet is not at the center of any of this. There is no center. We are simply here, in one spiral arm of one galaxy, surrounded on all sides by distances so vast that the word surrounded barely applies. The nearest large galaxy to our own is 2.5 million light-years away. The void regions between the filaments of the cosmic web span distances that would take our fastest spacecraft millions of years to cross. This is the context in which human civilization exists. This is the neighborhood. Now think about what it means to be the only ones here. Not definitely the only ones. We don't know that with certainty, but the evidence we have, the silence after 60 years of searching, the absence of megastructures, the lack of any detectable footprint from any civilization anywhere in the observable universe, points in that direction. And if it's true, even partially true, that we are alone, or nearly alone in this enormous cold dark space, then the weight of that is hard to overstate. Every mind that has ever wondered about anything, every question ever asked, every piece of art ever made, every attempt to understand the universe from the inside, all of it happened here, on this one small rock, in this one corner of one galaxy. That's not nothing. That might actually be everything. The numbers support this clearly. Earth has hosted roughly 100 billion humans across its entire history, each one conscious, capable of thought and wonder and creation. The total accumulation of human experience, every conversation, every discovery, every moment of joy or suffering, exists only because a rocky planet orbited at precisely the right distance from precisely the right star. The emptiness changes how you have to think about our choices as a species. Consider the crew of a spacecraft on a 40-year journey to the nearest star. There's no resupply, no rescue mission. What they carry is what they have. Every decision they make either preserves the mission or jeopardizes it. There's no margin. Damage that would be inconvenient in a normal setting becomes existential in that context because there's nothing else out there. Now scale that up. If the universe around us is genuinely empty of other intelligence, if we are the rare exception rather than one among countless civilizations, then humanity is that crew. What we carry is what exists. If we destroy ourselves through war, environmental collapse, or simple short-sightedness, there may be no one to continue the experiment. The universe does not back up its data. There's no redundancy built in. That's a genuinely different kind of pressure than most of us walk around feeling on any given day. Most people operate as though the systems we depend on, water, food, stable climate, functioning infrastructure, will continue because they always have. But that assumption is only available to us because the stakes feel distant. A spacecraft crew on a 40-year journey with no resupply would not have that luxury, and yet it's real. The Fermi Paradox isn't just a philosophical puzzle. It's a data point about how difficult it is to reach the stage we've reached. The Great Filter concept suggests that somewhere along the path from simple chemistry to spacefaring civilization, there is a barrier almost nothing gets through. If that filter is behind us, if the hard steps were the emergence of life, of complex cells, of consciousness itself, then we are on the far side of the most improbable sequence of events in the known universe. That's not comforting exactly, but it's something. Consider what it means to be rare in an otherwise empty cosmos. If the hard steps were behind us, if we cleared the most difficult barrier, then the universe is not set up to destroy intelligence by default. That distinction matters. What it isn't is meaningless. The instinctive human response to this scale is to feel small, and physically we are. But smallness in physical terms doesn't map directly onto significance. A universe 46 billion light-years in radius, composed mostly of vacuum and invisible matter and dark energy, producing almost no intelligence anywhere, produced us. That's strange. That's worth sitting with. The emptiness around us isn't evidence that we don't matter. It might be evidence of exactly the opposite, that whatever produced us was extraordinarily unlikely, and that makes what we do with the time we have carry more weight, not less. Now the harder question: do we stay or do we go? If the universe is mostly empty, and the distances are what they are, and we've seen what it would take just to reach the nearest star system, then spreading out into the cosmos is not a near-term option. It may never be a realistic option for biological humans at all. But the fact that the universe is structured the way it is, Matter concentrated in filaments, separated by voids, with no other detectable civilizations to compete with or learn from, means the choices we make on this planet are not just local choices. They're the only choices being made. There is no galactic council weighing in. There is no backup civilization watching to see what we do. We are, as best we can tell, running this experiment alone. That's terrifying. It's also clarifying. Go outside on a clear night and actually look up. Not at the bright stars in your field of view, but at what's between them. The dark between stars isn't just background, it's the void. It's the 80% of the universe's volume that contains almost nothing. It's the expanding distance between us and every other galaxy, growing faster than light can cross it. It's the silence of 60 years of searching returned empty. Every dark patch between those stars represents distances so large that our entire recorded history, every year humans have lived and died and built and destroyed, is not enough time for a signal to cross even a fraction of it. The night sky looks peaceful. It is not peaceful. It is incomprehensibly vast and almost entirely barren, and the light you can see is the exception to a rule that is mostly darkness. Here's what that actually means for anyone paying attention. We are rare, possibly singular, embedded in a universe structured to produce emptiness at every scale: physical, spatial, temporal, civilizational. The cosmic web concentrates matter into a small fraction of available space. Dark energy drives everything apart. The observable universe is a shrinking bubble. The silence of the sky suggests that minds capable of looking at all of this are extraordinarily uncommon. And yet here we are, looking, asking, trying to understand a universe that did not need to produce anything capable of understanding it. The emptiness is not a backdrop to the universe's story. It is the story, and we are a small, improbable, possibly singular exception to it, staring out into the dark and trying to understand what that means. I'm grateful you're here with me tonight for this exploration of one of the most fundamental questions we can ask about the cosmos we live in. We started with a simple question: why is it so empty out there? And the answer turned out to be layered in ways that are genuinely hard to sit with. 70 sextillion stars, billions of potentially habitable worlds, and yet 80% of the universe's volume is void. Not sparse, not thinly populated. Void. That's not a rounding error. That's the defining characteristic of the universe we live in. If you found tonight's journey worth taking, spend a moment hitting like or subscribing to the channel. It's a small thing, but it helps this channel keep exploring questions like this one. Questions that don't have clean answers but that matter anyway. We have a lot more to cover, and none of it gets less strange from here. Here's what I keep coming back to. The observable universe stretches 46 billion light-years in every direction. Beyond that boundary, there may be an infinite universe we can never see, and that boundary is shrinking. More of the cosmos slips beyond our horizon every year. The lights are going out, slowly, one by one, and there's nothing we can do about it. That's not a metaphor, that's physics. And somewhere inside all of that, on a rocky planet orbiting an unremarkable star at the edge of one spiral arm of one galaxy among hundreds of billions, you spent tonight trying to understand it. That's not nothing. That's extraordinary. Sleep well tonight, knowing that out there, Across 46 billion light years of expanding, mostly empty space, you are, as far as anyone can tell, one of the very few minds that exists to wonder about any of it.